So you guys, today we are going to be talking about fertilizer and the nitrogen cycle. Urea specifically here. We can broaden it out into other amendments if you want, but we're going to focus on urea because behind us what we have is a very cool demonstration, which I have not seen the results of, so you will be equally surprised as I am. We've got urea, we've got ESN, which is a polycoated urea, and we've got Super U, which is a dual inhibitor of nitrification and a urease inhibitor. These are all things that are funded by the OFCAF program, which is part of the reason that we're talking about it today. So, trigger warning, I am going to say the word enzyme, which automatically puts me to sleep. Please try to muscle through it. We won't talk about it for long. Okay, urea, put it on your soil. Urea, it's a pretty safe space. You're not going to lose anything. When urea is urea, it's staying as urea. There's no nitrogen loss. You add in a little bit of water and urease enzyme. That's the enzyme part, okay? It's almost over. I have like nightmares of like high school biology when we talked about enzymes and I couldn't hang in there. Okay? And it makes NH4, ammonium, positively charged. That's important. I'll tell you why. So you put your urea on and it turns into ammonium, but sometimes it turns into ammonia. Volatilization. So that's your nitrogen. That's a nitrogen loss pathway. You put your urea on, off it gases. What are the conditions for it to go in this direction rather than in this direction, a preferred direction, because this is what plants can take up, right? Urease enzymes. So if you're in a situation where you have a lot of urease enzymes, this would be high residue areas. For example, if you were broadcasting urea into a no-till system, you're going to have a lot of urease enzymes. So you should protect it, okay? If you have your urea near the soil surface, also very susceptible to volatilization. And I'll tell you why. So when urea turns into ammonium, this is your soil surface. If you have your ammonium down here, NH4 plus, the plus is important. Have I said that yet? You have your cation exchange capacity. Lindsay, can you come over here and hold that corner down for me? Thank you. Cation exchange capacity. What is the cation exchange capacity? It's negatively charged sites, soil, organic matter, and clay, right? Negatively charged. So it's like a magnet. Grabs that positive and it holds that ammonium in place. Okay? So if you have a big enough buffer between where your ammonium or your urea is converted into ammonium and the soil surface up here, so say 2.5 inches, key 2.5 inches, that's enough for that cation exchange capacity to grab onto that ammonium. If you're shallow, so if you only incorporate it an inch, you just scratch it in, or if you don't pack your slot, what happens, oh, Kristen, you queen. What happens is it volatilizes. Bye. There goes your nitrogen. Oh, thank you. So this is important. 2.5 inches deep. Pack your slots. Volatilization. I'm going to write it down. Yeah. Do you want me to spell? Okay, volatilization. So urea going into ammonium. This is the direction we want it to go. We sure as heck don't want it to go that way. That's money literally flying away, right? So we carry on the nitrogen cycle. Ammonium turns into nitrite, not plant available, nitrite with an I. And then it turns into, see, I ran out of room, sorry, nitrate, which is negatively charged. That means if you've got nitrate in here, the cation exchange capacity is not hanging on to it, because, you know, you remember playing with magnets when you were a kid, right? Two negatives, they're not hanging on to each other. So the nitrate is very susceptible to leaching. So if you've got nitrate down here in the soil profile, you get a heavy rain, a couple of inches, down it goes into your tile line or below the root zone. Okay, so nitrate is very susceptible to loss. And in this window between nitrite and nitrate is where denitrification happens. And denitrification, I hate using that word because it's very similar to this word here, nitrification. Denitrification is a greenhouse gas. So that's when your nitrogen in here turns into nitrous oxide. So nitrous oxide is 300 times more potent greenhouse gas than carbon dioxide. We really don't like nitrous oxide. It's terrible, in part because you're losing money, in part because climate change, right? So what are the conditions that cause this denitrification to happen? And I'll tell you about how I think about it in my squirrely little head, which is sort of scientifically accurate. So nitrate has 3 oxygens on it. 1, 2, 3. In cold, waterlogged soils. So think about waterlogged soils. This is the picture that goes on my head. You've got these little soil bacterias, and they're like, I can't breathe. And so they steal one of those oxygens, and this turns into nitrous oxide. Off it goes greenhouse gas. Boo! Okay. So the process that turns ammonium into nitrate, this is called nitrification. I need a different color. Things are getting crowded. Okay, nitrification. It's bacterial driven. Bacteria, enzyme. Urease. So what does OFCAF fund? A urease inhibitor. What does it do? It stops this process. So it keeps your urea as urea, where it's safe. It's not vulnerable to loss when it's in that urea form. When it's in sometimes they call it a pool. It's a pool of urea. It's safe there. So the urease enzyme is the one that converts it to ammonium. The urease inhibitor stops that from happening. Not forever, 7 to 14 days. Okay? The nitrification inhibitor works over here because the ammonium is a pretty safe form for your nitrogen to be in, especially if it's down here and being held onto by your CEC. So a nitrification inhibitor stops it at the nitrification stage. So it keeps it in that ammonium pool for a little bit longer. Because your nitrate, they're bouncing back and forth between those two forms. That's where things are most susceptible to loss. So this is where your inhibitors are working. In Super U, for example, Agritane Plus, another example. And so that's how your inhibitors work. Questions on that part?
Can I add something?
Yes, I would love it.
Okay, I just want to add something to denitrification specifically. So in my background, coming from Iowa, where we also have denitrification, our issues with cooler, wet soils, unlike here, are not as big of a deal. So when Rosie and I were first talking about planning out parts of this event, I was like, what? No. Denitrification results in N2 gas, Rosie. What are you talking about, this greenhouse gas nonsense? Because N2 gas is just nitrogen gas, and you are all breathing it right now. 70% of our atmosphere is N2 gas, okay? And ultimately, when nitrates and nitrites and ammonia, when that stuff breaks down to this inorganic form, denitrification all the way at the end of the cycle winds up as N2 gas. But the issue, as I learned, as Rosie taught me here in Nova Scotia, when you have these cool, wet soils, energetically speaking, ammonia, nitrates, whatever, when they break down, when they become nitrous oxide, energetically speaking, that's the easiest path to take. And so that is what is released instead of making it all the way to N2 gas, which I found that to be mind-blowing, okay? But this is all about where you are and where you farm, right? So I just think from my perspective, from an outsider's perspective looking in, it blows me away that like the energetic path of least resistance here is to just release nitrous oxide rather than make it all the way to N2 gas. I would say that your bacteria are lazy.
Points that I'm trying to make.
Maybe a quick question, right?
Yes.
Same hold true for cattle urea, like for urine, or is that?
For urine. Oh, great question.
What a great question.
So urine, there's often a lot of ammonium already in there. And I don't think it's in the actual urea form. So I don't think there's the urease enzyme. So like it's kind of like not quite this part. So when you have an organic form of nitrogen, so this is like compost, manure, biosolids, whatever, you don't have that urea piece. You have another color. You have this is my symbol for organic forms of nitrogen, because it also includes clover, right? There you go. So then you need microbes to consume it and excrete it, or the microbes die, whatever. So like that biological cycle of decomposition, and that's when you start to go in this direction. So it skips the urease enzyme, it skips the urea part.
But it doesn't matter what the form of nitrogen is, whether it's green manure, whether it's urine, etc. Ultimately, it may all break down differently, but once it gets to that inorganic form, it doesn't matter what you put down. You're still vulnerable to losing it. Once it becomes inorganic, it's inorganic. And at that point, you can lose it no matter what it was originally.
And inorganic nitrogen, which is also a term I hate.
Sorry.
Plant available nitrogen is my preferred term. Plant available nitrogen, ammonium, and nitrate. Those are our plant available forms.
Let me just jump in quickly. So I did quite a bit of work on cow urine, and not my best time. But as soon as cow urine mixes with feces, then you get that process happening. So if you have a dairy where everything's going down a single drain, then a lot of it is volatilizing right away. But on its own, it doesn't volatilize as quickly.
So if you can it, right from the source.
Yeah, that's what I was doing.
So polycoated urea, I like to think of it like chocolate covered almonds, obviously. Why would you not think of it that way? Here's your chocolatey coating, which is the polymer, and inside is your urea pearl. And we actually have a cool little demonstration here before we even get to the bigger demonstration. So urea is this polymer coating, okay? So the brand names that you can buy here in Nova Scotia, I'm pretty sure are Pure Yield or ESN, depending on who you buy your fertilizer from. That polymer coating is it's literally the chocolate on the almond, and that slows down that urea, starting the whole process that we just talked about. And so standard times from when that urea is like all protected in its little shell to when it like goes out into the wild is like 45 to 60 days. So if you've got polymer coated, I personally would never recommend to use it on anything with a short nitrogen uptake window. So like I would not use it on any spring grains, for example. I would use it on pumpkins who need nitrogen later in the season. I would use it on corn. I would use it on potatoes. I would use it on storage cabbage. Those crops that have a nitrogen demand later in the growing season. I wouldn't use it on onions because it'll slow down them tipping. Any other crops anybody's curious about whether you'd use ESN? Christmas trees, great question. I don't know what the nitrogen curve looks like for Christmas trees, but to digress to Christmas trees, when they fertilize Christmas trees, basically what they're doing is they're walking along and they've got scoop up a handful and they sprinkle it underneath the Christmas tree. And it's like trees below this side is like 1 handful, trees above that side is like 2 handfuls. It's a very accurate system. But that's urea typically just sitting right there in the soil surface and going up into the atmosphere. So I would protect it at the very least. I would use like Super U or something like that to protect it. Okay, so this is your Pure Yield or your ESN, and so it's got this polymer coating. And so when it leaves the factory, thanks Delia, it is perfect. It is pure as the new driven snow. There are no nicks on that polymer coating. But in between the factory and your farm, it probably goes through several augers, right? And I'm sure your auger is not very rusty, but I'm not saying that any of the augers along the way weren't rusty. And so as soon as you start to nick that polymer coating, water gets in, and all of a sudden you're just buying real expensive urea, right? So now on to our cool demonstration where we have some ESN. So nice thing that I like to do if I were to have bought some ESN and I was suspicious that there might have been some rusty augers in there, you could count out 100 pearls, and you sprinkle it into a jar of water. You'll notice there's a few pearls floating on the surface of the water there. So this is our rusty auger nicking up our polymer coating. That's perfect, thank you. And we're gonna see if there's a difference. And so last week we did ESN, not rubbed, and then the ESN that had the sandpaper. You can see the sandpaper one, you've got more polymers coating, like floating. You can see them sticking together in there, and so that's how you know that it's not really working. So like if you do a jar test at home with your ESN just to kind of see how it is, that would be the cue. So if you think about if you put your ESN on the soil surface, we get an inch of rain in maybe 12 hours, so it's kind of a little bit faster than that water can get into the soil. And so what happens is the water starts to go over the soil, carrying your ESN with it and dumping it in a ditch. You read a news story about that every once in a while about, oh, I went out to my field and all of my polymer coated urea was in the ditch. So personally, I would not surface apply. So going to Christmas trees, ESN, I would not surface apply ESN because it floats and that sucks. I would put it in the ground. You probably don't have to bury it quite as deep as you would your untreated urea, right? Seed coated, or sorry, it's great. You can place it with the seed, for example, because it won't damage the seedling. Thank you. Yeah, so because it's in that polymer coating, it slows the release of that urea, so it's not going to damage your seedling. So if you're going to use ESN, I would put it in the dirt. I wouldn't leave it on the soil surface.
So what starts breaking down the polymer coating?
Physical damage, typically.
Rusty augers.
Rusty
When
augers.
you apply it, like, is that when you're starting to count, okay, that's day one when it's going to start breaking down, or is it day one when it gets manufactured?
Great question. So if it's not damaged, day one, you could consider it in the field. And what breaks down that coating? Time, temperature, moisture. Moisture.
But doesn't that happen, doesn't time and moisture happen in the process between it getting manufactured and getting to a plant and getting it taken to you?
Ideally, there should not be a lot of moisture happening in that transfer process. Like, it's not like you're leaving it outside in the rain, right? You know, so it's...
But the older the product,
Yeah.
right? So if you have a bag of ESN hanging around for 3 years in the back of the shed, my guess is it's not going to be worth much.
So you'd want new product from your supplier, like
Every
you
year.
wouldn't want it held over or whatever.
Yep.
Essentially is what I'm asking.
Yeah. Okay, so we've been talking about surface applied urea, which we got back here. So the other thing to think about, if you have surface applied urea and your weather predictions are accurate, your urea is very soluble, right? So if you get some rain, that urea is going to solubilize and it's going to go down into the soil profile. And if you want it to be stable in there, you really want it to go down to that 2.5 magical number, 2.5 inches deep. So that means you need at least 1/2 inch of rain for it to get deep enough that it's going to be in the soil and not volatilizing. So now I'm going to tell you what we did behind me. So what we did is we're trying to do proof of concept of that whole urea process that I was explaining to you. So what we have behind us, we've got urea, we've got Super U, which has both inhibitors on it, and we've got ESN, which is that polycoated stuff. And then because in residue, there's that urease enzyme, so we're testing that like concept as well. So we've got bare soil or bare-ish soil, and then we've got soil where we sprinkled a little extra residue, just because we're hoping this is going to work. It's totally going to work. So we have bare soil on this side. We've got residue on that side. We've got all 3 fertilizers. We also have no fertilizer because you kind of just want to know. And then some of them have gotten 1/4 inch of rain. So in theory, not enough to drive it deep enough into the soil profile to prevent volatilization loss. And then the last 2 plots here, we have urea and 1 inch of rain, which should be enough to drive that water deeper into the soil profile. Okay, so you've got a little map in front of you. That dark blue, that's over here. And then that way is north, da, 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 da. Okay. So the other piece that I didn't mention, another thing that drives volatilization is wind speed, right? So if it's a windier day, you're going to have more volatilization. In the Maritimes, it is pretty windy pretty much always. Turns out, another thing I learned, the average wind speed throughout the month of August, because there's a weather station over there, was about 4 kilometers an hour. So down below here, so there's a big old formula that converts what we're going to find under the buckets into the amount of ammonia loss. And so the difference between 4 kilometers an hour and 5 kilometers an hour of wind speed, it almost doubles your volatilization loss. It's 1 kilometer an hour. I did not expect that. Very interesting. Okay, so underneath these buckets is a stake with something called a Dositube on it, which is basically a little glass cylinder. It used to be purple, and now it's turning yellow, which is measuring the amount of ammonia that's been lost through volatilization. Okay, so you've got what we did here. Which one do you think has lost the most ammonia?
1 inch of rain on the bare ground.
1 inch of rain, bare ground? All right, Phil, come stand next to 1 inch of rain on the bare ground. This is going to be like a big reveal.
The opposite, like on the bare ground with no rain or minimal rain.
Perfect. Bare ground, urea.
Yeah.
Okay, bare ground, urea, no rain. That's over there. Terry, you go stand next to that one.
Okay, where's that? Second from the end?
Lindsay, you want to find third from the, yeah.
I'll go bare ground, quarter-inch rain.
Bare ground, quarter-inch of rain of urea. All right. Who else? Got any other guesses? Remember the urease enzyme, lots of that in residue. Hint? That was a hint.
More residue is
More. Yeah, more loss. So which one are you guessing?
I'd say the rain with the residue
Rain with residue and,
and urea.
okay.
You didn't talk about is the residue tying up, so it's technically.
Oh, I know. This is what I'm like. This is my explanation if it doesn't work. It could still be there, yeah. Do you want to go stand next to, would you say residue, urea, quarter-inch of rain? That's here-ish. Yeah. Government rates. I don't get government rates. All right, least loss. Which one do you think has the least loss, the lowest amount of volatilization? ESN with rain. Okay, with residue, without residue. Without residue is on this side. Here.
Residue, no fertilizer.
Yeah, what about no fertilizer? Come on, who's gonna go stand next to no fertilizer? Colin's gonna stand next to one, you get to stand next to the other one. Actually, there's no fertilizer with rain, no fertilizer without rain as well. Where's Georgia? Oh, okay. Okay, Lindsay, can you help those guys figure themselves out? All right. Least, we've got no fertilizer, we've got ESN. I need a least on a Super U, please. You guys don't think that stuff's gonna work, Krishna? You can decide whether you want rain or no rain. All right. Yeah, okay, everybody go stand next to one now. Seriously, go pick one. All right, Philip is bare ground urea, 1 inch of rain. I'm expecting low losses here.
What am I looking for?
You take the brick off. Take the whole bucket. Whoop! Oh, don't break it! You got it! Okay, this is what it looks like. This is your Dositube. It used to be purple. See? This is your Dositube. It used to be purple, and where it's measuring volatilization, it should be turning slightly yellow. And so you can see that there is a little gradient on the side, and it's going to look real weird because it's a logarithmic scale, so it's not like even increments. That's on purpose. They did the math. Okay, so you see, is there any of that not yellow? No, that's all purple all the way down.
Purple all the way down.
Purple all the way down. Don't take your Dositube off of the stake, by the way, because Lindsay's going to write it down later. No losses. No losses. If it's urea on the surface, which is where you typically expect to see your losses, is urea on the surface, but with 1 inch of rain, it got down deep enough that there was no volatilization. Yay! All right, bare ground urea, 1/4 inch of rain. I'm expecting that to be a little higher. This is bare ground urea, 1/4 inch of rain. So maybe just enough rain to get it into the soil profile, but maybe not deep enough. Oh, you got to turn the doohickey a little bit here.
Yeah, no, I can see it. It's purple all the way to the bottom.
Purple all the way to the... God damn it.
Guess
right.
I was right.
Also no losses. Also no losses. All right. Well, it was 1/4 inch of rain. It was just not very much. Okay, with residue, how are we doing over there? Any yellow?
Purple is just going to there.
Check from the bottom there.
there,
Oh,
there,
you
yeah.
got some. Oh, you got some. Just a very little bit. Okay. 25 ppm, that's the measurement, 25 ppm. So if you look at your paper, Krishna, what's 25 ppms there with 4 kilometers an hour? 1.3? Yep. You only lost a kilogram of nitrogen. That's not bad.
In that little spot.
In that little spot.
A kilogram?
Kilogram.
Kilogram. Did I say what I said, kilogram?
You should kilogram, yes.
Well, yeah, it's on a like per acre basis.
Oh,
Yeah.
okay.
God. All right, 1/4 inch of rain urea. But with our Super U, Krishna, did we lose anything there? Oh, you haven't gone yet. We have not, I just realized. Sorry about that, you gotta keep me on track. Oh, you gotta turn it here like this. Oh, nothing. Nothing, no losses. Super U, great, that's what we expected.
Yep.
Great. Sorry, I did skip, I forgot your name. Murray, I forgot yours. Sorry, can you do a big reveal? So this is, wait, tell them what you got. Urea on residue, 1 inch of rain. So you would expect more urease enzyme activity, but because it went deep into the soil almost immediately after application, I'm hoping to God there's no loss. Ooh, and we're right, no loss. Good job, Murray.
Mary had a lot to do with that.
I hope you're proud. All right, what do we got here?
Super U on bare ground.
Super U on bare ground. So wait, what are we expecting? Should be no losses. That's what I'm hoping. All right. No losses, no losses. Great, good. The thing works. What about you, ESN? What are we expecting? Shouldn't lose much. Turn it around. There you go. Purple all the way down to the bottom.
Yep.
No loss. Great. Thanks, ESN. Here, I'll take that. Bare ground. I'm hoping this is also 0. Oh, you can still see some of the little ESNs on the soil surface. That's interesting. You can't for any of the others. What do we got? No loss. Good job. All right, residue, no fertilizer. I'm hoping you can both do them at the same time. I'm hoping both of you don't have any losses because there's no fertilizer. Great, no loss, no loss. And that was with rain, no rain. Also, I'm hoping you guys are no loss.
These are both controls, right?
These are both controls, no rain controls. No loss, no loss. All right, good, good. We're not getting any volatilization where there was not any fertilizer. I was a little worried.
All right.
Okay, here, who knows what's gonna happen here?
Which one's that one? Urea, bare ground, no rain. What have we got?
No loss, god damn it, that didn't work.
I think it's wrong.
Oh, I think it's wrong too. I would have expected more loss to happen there. You came and watered all the, let's go! It's because I sent you all the weirdos, isn't it?
Residue, urea, no rain.
And we've got no loss. Again, not what we expected. But, I mean, it goes to, Georgia, remember when I was like, remind me to say that thing? This is where I'm going to say the thing. So this is fertilizer applied to the soil. There's nothing there to take it up, and it's been dry as heck, right?
When was it put down?
Last week. Great question. Last Friday. So it's been 6 days.
My next question is,
Yeah.
see all the holes in the bucket. What happens if 3 days ago you got a rain you weren't expecting?
Okay, so the actual protocol is if there's a rain, it's not enough to let like the actual amount of rain in. And so like if we were to be doing this over 3 weeks, which was what the original experiment was, which I then bastardized, not a swear word, you're supposed to move it each time it rains.
Okay.
So what I'm kind of hoping is going to happen is you guys are going to be so excited about this experiment, which only sort of worked, is that next year you say, hey, Georgia, can I have those buckets and a dosimeter? I want to see how much nitrogen is losing in my field. And you set up this little experiment in your fields and you monitor it and see what happens. Wouldn't that be cool? They did this in Ontario, and so your volatilization losses are going to largely happen those first 3 weeks. Your biggest windows is usually in that 7 to 14
What
days.
about the fact that the soil is so dry?
So dry.
You're adding water, and maybe it's not having the same effect it would normally have in a regular season.
Great question. So the water that we added, we were careful the way we did it so that it was like actually soaking in. So it should be somewhat similar as what you would expect from a rainfall. Yeah.
I'm just wondering, I guess in my question, and I don't know either, I'm coming into this just like everybody else is, but I look at this and I'm thinking to myself, we should have seen some losses with this one here.
Yeah.
And I'm just wondering if there were losses and we're not going to see it because it escaped too quickly for the what is that, Dositube to actually catch it.
Oh, interesting.
I'm wondering if the Dositube just wasn't actually able to capture the gases. It escaped through the holes before it was able to measure it.
I don't know if you guys seen
I
any
caught
of
it here.
Got it here. Thank you.
the Atlantic Grains Council did some trial work with Dalhousie in Truro and did this on a corn scale and seen similar results. I don't know if that's public knowledge, like if that's something that we can reference to this, to that, but similar.
Where's
like,
Caitlin? Do you know about the Atlantic Grain Council and did they do it in corn with Dositube?
yeah,
Nice.
Yeah.
All right, so that report will be coming out
that was last year they did
last
it.
year.
Yeah,
So-
actually there's a podcast episode on it.
Yes, Caitlin! Does everybody know about Caitlin's podcast? Because it is top notch. Highly recommend. Even if you don't grow field crops, it's worth a listen. I really do
Check
love
out
it.
that episode because it's probably all about that trial. that they did.
Awesome. So normally when they measure greenhouse gases and stuff in a field, it is a $20,000 system. $5 for that bucket.
For the slow release stuff though, how, like you're talking only 6 days that it.
We did. Yes, great question. And so in theory, like if we wanted to kind of see it, we would leave it out there for 3 weeks.
Well, I'm dying to know what's under the rest of these buckets.
Who has it? Have you done yours?
I did mine.
You did yours? Okay. Will, what do you got? Wait, you got Super U, bare ground, no rain. And you can still see, look, you can still see the little granules right there. So no rain, which meant that, yeah, no rain, so that meant that that urea is still in the urea form, and you can see it on the soil surface here. What about very stable in that urea form if it's not volatilizing. But that's just a little bit of moisture. It's not necessary. It's not typically a lot of moisture. Nada, nothing.
And you watered it after you applied the fertilizer?
Yes, yeah. Not these ones though, because this is dry. Yeah. Good question, good question. We put thought into this. And so you've got ESN, and again, you can see the ESN pearls on the soil surface here, which is probably worth coming and taking a little look-see. No losses. And what about you? ESN, no losses, which is also what I expected. So this sort of worked, only a little bit. I was expecting much bigger losses to happen than just the one little bit. And you were 1/4 inch of rain, urea.
You proved that just don't do this, everything else is fine.
All right, that's true. And my work here is done.
The question is not just about losses, but were there any gains to the plant because it's all still on the surface after 6 days.
Great question. So she says, is there any gains to the plant? Because if it's sitting on the soil surface, that's as a urea prill or as an ESN prill, the plant can't take that up. And that's true. But the ones that are on the soil surface is the ESN and the Super U in the really dry environment. And apparently the urea is not on the soil surface in a real dry environment. So like you need that water to get that fertilizer to the plant roots anyway.
Where does the coating go? Where does that polymer coating go? Has there been any research into where that stuff goes, if that's long term going to affect us?
Great question. Some people often get really worked up about it, honestly, because they're like, I'm putting plastic on my field. But if you were putting on 100 pounds of ESN, 100 pounds of nitrogen, that is ESN, sorry about that. So that's, ESN is 44% nitrogen, a little bit less than urea because of the polymer coating. So that's like you're putting on 440 pounds of ESN, so 100 pounds of actual N. You know what that equals and how much plastic? 4 pounds of plastic. So like, don't get me wrong. Do we want to be putting plastic on our field? No, not really. Does agriculture have a plastics problem? Yeah, like you've got silage plastic, you've got drip tape, you've got black plastic. Like, there's a lot of plastic going on your fields. This is not the biggest and the baddest of the animals.
There's also PFAS.
Poly.
Yeah, I don't know what it is for in English, but that's gonna be a real big problem in agriculture, right? In the whole world.
Yeah, so he's talking about PFAS, which is poly something. If my husband was here, he'd be like, "Oh, you mean this thing?" He's like that. He's not actually here. PFAS, it's a plastic byproduct, and it is a concern, but this is such a small amount that it's like the dose makes the poison.
Yeah, but time and time, year after year, it's building up, and it's not breaking down.
Well, so this stuff does degrade. So the polymer coating does degrade. So it's a physical and it's a biological process, and eventually it does go away. It just takes a while. 5 years.
What does it break down into?
Other organic ingredients.
Organic or inorganic?
Yes, organic. All right, any other, oh, the other thing, the thing that I said that I wanted to mention. Last thing, sorry about that, this took a little longer than I expected. We saw the urea was sitting here on top of the soil surface. So something to think about here. We've had a really terrible growing season. You fertilized your crops like you would expect to have a crop that grew. And so all of that nitrogen is still sitting in the soil. And so at the end of the growing season, when do we have our greatest amount of nitrous oxide emissions in Atlantic Canada? Post-harvest, because you have all of your residual nitrates of what the plant didn't take up. So this year in particular, I know it's a really hard year, but think about all of that nitrogen that's left in the soil that will become a greenhouse gas, will go into the groundwater, and all of that money that you're losing. This is the year to plant a catch crop, if we get any moisture. Fall rye, oats, just to soak up some of that residual nitrogen and use it as a credit next year for your cash crop. That was the point I wanted to remember to make.
I do have one comment about the plastics.
Yeah.
We talk about plastics in agriculture, and it is a problem.
It's a problem.
But you use the example of silage plastic, whether it's bunker cover. Yeah, this is the example. Those are necessary evils.
Yep.
ESN's not a necessary evil.
I personally would rather see a split application than using Super U or ESN.
But the problem is with some of it is like the ESN or the Super U is like $400 to $500 more a ton at times, which can affect your.
Again,
our governments were willing to pay a subsidy on that, put the plastics in your ground for something that's not a necessary evil.
It's all in how you choose it. Like, I'm not recommending one or the other. Everybody makes their own decisions for themselves. I would always recommend a split application of nitrogen over using fancy fertilizer, because especially on our sandy soils, that just makes way more sense. And you know, the cost of running a tractor over a field again, it's cheaper than the ESN.
Everyone, we're gonna have to get moving. We can continue the discussion around lunch. Let's give Rosie a round of applause.
Great job, Rosie. Great.